dragonflies the size of hawks, centipedes larger than humans, a strange menagerie of giant insects and amphibians reigned over the Earth 300 million years ago. Over time, these huge creatures shrunk in size or disappeared. The reasons for their progressive extinction remain controversial. $358 million years ago, the continents came together to form the supercontinent, Pangaea. This was the beginning of the Carboniferous period. Oxygen levels in the air were much higher back then, 35% compared to today's 21%. For the first time on Earth, giant trees stored carbon dioxide and released oxygen in abundance. Human beings would not have survived in this high oxygen atmosphere. But for some swamp dwellers, it was ideal. Like Arthropleura, measuring up to 10 feet. This long-lost cousin of the centipedes was a herbivore. Or Meganeura. With a wingspan up to 25 inches, this member of the dragonfly family is the largest known flying insect ever discovered. A tireless predator. It had no airborne competitors at the time, since birds and flying reptiles didn't exist yet. The high oxygen levels in the atmosphere give the characteristic sepia color to the sky during the Carboniferous period. Oxygen also makes the air extremely flammable. Such a hostile world is hard for us to imagine. Lightning storms could set aflame the immense forests and their inhabitants. During this period, not a day went by without huge forest fires, and yet giant insects thrived. Later, when fires became less frequent, these astonishing creatures simply disappeared. Scientists are trying to determine what caused their extinction.
There are several possible culprits. In fact, it's a bit like an Agatha Christie novel, when there's not one, but several murderers. It's our job to take the clues we have and reconstruct the investigations in order to come up with the most likely scenario.
While we've known about giant insects since the 19th century, paleontologists did not understand why they had disappeared. For a long time, a change in the composition of the atmosphere was the only explanation. But at the beginning of the 21st century, the discovery of fantastic fossil insects and their predators opened up new possibilities.
While that's a wonderful hypothesis, and assuredly something was preying upon these giant insects, we don't have great evidence for it.
Around the world, American, European, and Chinese scientists confront the old theories using new fossil discoveries unearthed by groundbreaking technology to try and explain why these giants became extinct. The earliest giant insect fossils were found in the French region of Allier in 1880. Under the surface at this pond were the remains of animals that had died 350 million years ago during the Carboniferous period, Meganeuras. Now extinct, these tireless predators are the largest flying insects that ever existed. This abandoned industrial site was an important coalfield in the 19th century, and as the coal was dug out, fossils were discovered close to the town of Commentry. The owner of the coal mine, Mr. Moni, gave his name to the specimen that is preserved at the Natural History Museum in Paris, Meganeura moni. André Nel, a paleontologist whose speciality is early insects, watches over this valuable piece.
Miners would look for fossils to make a little extra money. And one day, when they were opening slabs, they came across this animal. Unfortunately, when they were digging it out, they hit it 4 times with a pick and we lost its head. They were the super predators of the time, predators of other insects that were also very big.
These large-sized fossils are quite exceptional. While thousands of insects were found on the site of Carboniferous, only 5 Meganeuras were ever discovered.
Meganeura, like all other insects, had 4 wings, 2 on each side attached to the thorax in the center. In front you had a head with big eyes because it was a predator, so its eyes, just like modern dragonflies, were used to see its environment in 360 degrees, so possibly even behind the animal.
To better understand how this extinct animal once lived, we must step back 300 million years in time. This is what the French region of Allier would have looked like then. A giant swamp scattered with cypresses. Humidity at nearly 100% made the atmosphere dense and allowed Meganeura to easily carry its heavy exoskeleton into the air. It is part of a genus that is extinct today, but it looks much like modern dragonflies and is part of the same Arthropleura superorder. With wings that functioned independently of each other, Meganeura was agile in flight, but unlike its contemporary cousins, it couldn't fold its wings. Faced with this efficient airborne predator, vegetarian insects such as Paleodictyoptera had to keep themselves out of sight. By comparing its anatomy to modern dragonflies, we can guess at Meganeura's main physical characteristics. 1, it could fly over 40 miles per hour. 2, it was a sight predator. Its head was independent from the rest of its exoskeleton, so it could keep it still while flying and focus on its prey. 3, it had a huge appetite. It could eat its own weight in food every 30 minutes. To catch all this food, Meganeura had an array of attributes identified in fossils. But what might explain its giant size? Away from the public is the museum's library of species, where they keep the specimens that scientists study. Here we find Meganeuras and their prey, both reaching impressive sizes.
So here you have an example of a Meganeura, on which we see the base of its wings, the thorax, but what is most spectacular are the 4 legs equipped with strong spines that were used to stab prey. But the Meganeura's prey were also large-sized insects, like the Paleodictyoptera. You just have 1 wing from here to here, so you can imagine the whole thing. These were Meganeura's prey. They were big guys too. Big insects to escape big predators. So in this case, we have an arms race between predators and prey.
But this battle to be the biggest between Meganeura and its prey seems to have had its limits. Otherwise, paleontologists would certainly have found even bigger and more terrifying flying insect fossils. Most of Meganeura's day was spent looking for food, since its metabolism required a lot of energy. According to scientists, the huge size of insects during the Carboniferous period was possible because of the high levels of oxygen in the air. Insects don't have lungs, but instead use a unique system of tubes, trachea, and tracheoles to bring air directly to their organs, including their digestive system. The downside to this system is it lacks efficiency. Air travels through the tissues in the form of gas. The bigger an insect is, the more oxygen it needs.
It is very strange that these animals reach these sizes, because nowadays we do not have such big insects. And at the time of the dinosaurs, when we had large vertebrates, insects were much smaller. It turns out that in the Carboniferous period, for reasons linked to geochemistry, the oxygen rate in the atmosphere was higher than it is today, which encouraged the development of animals such as the large insects.
Meganeuras could not survive in today's atmosphere because not enough oxygen would reach their organs, including their brains, and they would faint. Since the beginning of the 20th century, scientists have proposed a link between the size of insects and the concentration of oxygen. But it wasn't until 2007 that an experiment finally proved it. In the Chicago suburbs, the Argonne National Laboratory houses the United States' most powerful synchrotron, a scanner that generates the brightest X-ray beams in the Northern Hemisphere. The distance around the particle accelerator is more than half a mile, so Jake Soka, the scientist in charge of the study, uses a trike to get around. Today, live insects are being put under the scanner.
We use the idea that you can take living insects and make inferences about insects that existed in the past. What we're trying to do in this study is to test an old hypothesis that the amount of oxygen in the atmosphere is what limits insect body size. So the idea with this hypothesis is that when you have more oxygen, your insects can get larger, and when you have less oxygen, insects will get smaller in response. But no one had really ever tested this hypothesis before. So we use synchrotron X-rays to look inside the animal to study the dimensions of their tracheal system.
This particle accelerator generates extremely intense and focused X-rays that pass through the insect's body.
Our purpose is to see the tracheal system in action, and some of the tracheal tubes are really small, and we want to see it in the living animal. So this is really the only technique where we can do all of those things.
For the first time, scientists are able to actually observe an insect breathing.
Would you turn the beam on?
Using this experiment, they discovered that crickets not only breathe passively, but also use their whole bodies to carry air to their organs.
And you can see that bubble in the gut moves forward to the head, and it moves backward. And every time it's doing that, it's synchronized with the compression of the tracheal system. The movements that you see here are not a passive effect. This is an active movement by the animal, and it's the ultimate cause of it are contraction of muscles.
Just as this cricket contracts its digestive system to send air to its organs, Meganeura would have contracted its abdomen to absorb the thick Carboniferous air. The elastic exoskeleton would resume its shape once the muscles had completed their action. But beyond the discovery of this internal movement, what interests Jake Soka is the space occupied by the respiratory system within the insects' bodies. He has compared beetles of different sizes to study the link between their size and that of their respiratory system.
And what we found is that the tracheal tubes take up a larger fraction of the body as you go from smaller to large than you might expect. So what we think, based on the study, is that if you would make this even larger, so if we would scale this up farther and farther, eventually you reach a limit where you can't stuff more tracheal system inside the animal because you have to have other things like muscles and gut and nervous tissue, fat bodies, things like that, that are all important for the physiology of the animal. You can't just have one big tracheal system.
The higher oxygen concentration of the Carboniferous period meant that insects required fewer respiratory tubes and could therefore grow to a larger size. But with the modification of the atmosphere, the giant insects had to reduce their size over millions of years of evolution. And not all of them survived these changes. 290 million years ago, during the Permian period, oxygen levels decreased from 35% to 23%, close to today's level. Pangaea had already formed a supercontinent extending from one pole to the other. Surrounded by a single ocean, it was subject to extreme climatic conditions. The heart of the continent suffered drastic temperature changes, and deserts appeared. But at the equator, heavy rainfall allowed the great forests from the Carboniferous era to survive. During this period of major climate change, punctuated by the monsoons and the warming of the atmosphere, a living fungus appeared on the bark of trees. This tiny mushroom uses an enzyme to break down wood. Gradually, plant debris and dead trees decompose and no longer build up on the ground to form coal. The fungus stopped the accumulation of carbon on the ground, and instead it was recycled into the atmosphere. The proportion of oxygen in the air decreased gradually, with major consequences for the environment. This transitional period brought about the demise of Arthropleura, a distant relative of the centipedes. But why did the first giants of the Carboniferous period disappear? Could their lifestyle be responsible? In 1977, Arthropleura fossils were found in Autun, in the heart of the French countryside. The slag heaps surrounding this former mining town are hallmarks of its industrial past. In the local Natural History Museum, tribute is paid to the miners who discovered fossils while they were working. Among them, this impressive set of footprints, the most important ever found in France. They're examined by Sylvain Charbonnier, a specialist in arthropods, the family of invertebrates that includes insects and centipedes.
Here you can see a set of tracks. You have two trails that are parallel. This was made by an organism of quite a respectable size, an animal that must have measured around 3 feet long. It's just a fragment of the track that was probably much bigger.
Unfortunately, no adult-sized fossil has been discovered, but the paleontologists have found many smaller specimens in these coal deposits.
You can see here what this little creature looked like. These are juvenile specimens, which are tiny. Here's a complete specimen with its shell that is well preserved, so obviously this organism, as it grows, will produce larger trails when it moves.
Arthropleura was rather similar to modern centipedes. It could reach 10 feet in length, and it crawled on the ground or up trees in search of food. Life in the rainforest during the early Permian period was quite similar to that of the Carboniferous period. And there was enough oxygen in the atmosphere for Arthropleura to thrive and face unexpected predators such as Eriops. This amphibian locates Arthropleura using cells in its skin that detect vibrations on the tree trunk. But Arthropleura had a considerable advantage. The claws at the ends of its articulated legs allow it to grip the trunk, and its protective shell shields it against attackers. Arthropleura's disappearance may not have been caused by predators, but by decreasing food supplies. This creature was a herbivore. At the time, it would have had plenty to eat.
At that time, the vegetation was equatorial or tropical, so it was an extremely lush vegetation with a great variety of plants. These plants are in fact the origin of coal. Arthropleura lived in this forest environment. You also have on the other side trees and leaves that were found in Arthropleura's stomach contents. So it probably fed on these tree branches. Did they eat from trees lying on the ground or did they climb trees? These are hypotheses we will probably never know for sure.
These fossilized plants have been so well preserved that they still appear alive. But as they began to disappear, Arthropleura had to adapt.
This forest environment will tend to dry out at the end of the Carboniferous. The climate will change, the vegetation will disappear, and Arthropleura will lose its food source, which is probably one reason that explains its extinction.
Over a period of 10 million years, the atmosphere and the climate gradually changed, bringing about the demise of Arthropleura. The most recent fossils we have date from about 280 million years ago. Evolution could have retained smaller and more energy-efficient insects. However, in 2009, scientists were surprised to find new Meganeura fossils in the south of France. These specimens, discovered on sites dating from the end of the Permian period, prove that the declining oxygen rate cannot be the sole explanation for the extinction of giant insects. What clues did these unexpected fossils reveal? These deposits are scarce. Scientists know of only about 15 of them in the world, and like here, they've not been all fully excavated. This beautiful landscape with its typical red rock is located less than an hour from the French Riviera. This is one of the sites excavated by André Nel.
Here we are, 250 million years into the red continental Permian. Red Permian because the rocks have become oxidized. The iron is oxidized and has become red. So we are dealing with an environment that is extremely rich in organisms that have left their impact but few visible fossils up to now. In any case, in this deposit. But fortunately, fossils have been found in other deposits.
It's in a similar geological layer that insect fossils from the Permian period were discovered in 2009, close to the French city of Montpellier.
For a long time, we thought that these giant dragonflies had existed during the Carboniferous period and at the beginning of the Permian, but they no longer existed towards the middle and end of the Permian. But we were surprised to discover dragonflies that were as big as those from the Carboniferous.
Paleontologists were perplexed, since the level of oxygen had already decreased by that period. In theory, giant insects should have disappeared, but the specimens of different sizes conserved in André Nel's laboratory in Paris proved that they were still around.
There are tiny wings with the Meganeuras like this one here. This is the size of a modern dragonfly's wing. We have much bigger species. Here is the rear wing of another Meganeuridae, another species. This one too was a giant. We have bigger ones, but only fragments. This here is a piece of Meganeuridae's wing. The size is comparable to that of the Meganeuridae of the Coniferous. We estimate that its wingspan is around 23 inches. We see that with these animals there is great diversity. It's during this time that they become the most diversified. We have small ones, medium ones, big ones, and very big ones. This means they had not really become extinct at this period. This does not sit well with the scenario of extinction due to the decrease in the level of oxygen.
These recently discovered species of Meganeuras found in France have also turned up in the United States. Evidence of their existence is accumulating. Here is what the Earth looked like during the middle of the Permian period, a hot and humid world covered with tropical forests. With an oxygen rate just slightly higher than today, one animal species survived against all odds, Meganeuras, represented by this Meganeuropsis. This specimen, discovered in Texas, is as large as its French cousins. But how can an insect measuring nearly 2 feet survive breathing air that was much poorer in oxygen than in the past? Did it have an advantage that Arthropleura did not? The Meganeuropsis fossil was discovered in 1937 next to Kansas City in the USA. Professor Michael Engels is a paleoentomologist who has worked at the University of Kansas for the past 20 years. Author of the definitive work on the evolution of the insects, he is also the head of this collection, containing 4.7 million specimens, most of them contemporary insects.
These are some of the large insects that occur today, large moths, stick insects, beetles, dragonflies, and damselflies. And while they're pretty impressive in their size, none of them can compare to the giant insects of the past.
According to Engels, one asset which might have enabled Meganeuras to survive during the Permian period, despite the lower oxygen levels, is the movement of their wings.
You would have an easier chance getting a large flying insect than you would a large insect that doesn't fly. Wings are vital not only for the movement of the organism, but as the muscles contract to move the wings up and down, they actually press up against the air sacs and move air through the body. Flight actually confers an advantage to the giant insects in the fact that the actual movement of the flight muscles helps to support the metabolically active tissue within them by getting oxygen into an area where a wingless insect or other arthropod would not be able to.
This full-body ventilation could be the secret to Meganeuropsis' survival. The movement of its wings quickly brings air to the trachea, which then supplies the organs with oxygen. While the ground-dwelling giants of the Carboniferous period disappeared, this advantage would have allowed Meganeuras to continue ruling the skies during the Permian period, remaining at the top of the food chain in the swamps. This Diplocaulus, a now extinct amphibian, has no chance of going unnoticed, betrayed by its need for air. Meganeuropsis sees it as soon as it leaves the water surface, thanks to eyes that are extremely sensitive to movement, shapes, and colors. Meganeuras were the super predators of the time, and their wings enabled them to survive despite falling levels of oxygen. So what caused their extinction? No Meganeurid fossils have been discovered from after the Permian period. Today, scientists still don't know exactly when they disappeared, but other large-sized dragonflies survived the next 130 million years. To explain the extinction of these giants, scientists are now contemplating the emergence of new predators. While insects were the only flying creatures during the first part of their history, other animals took to the skies during the later Permian period, between 300 and 250 million years ago, of what was to become, eventually, Europe. Jean-Sébastien Steyer, paleontologist at the Natural History Museum in Paris, is the leading French specialist in early vertebrates. He has come to the legendary Paleontology Gallery to collect a very important specimen for the study of insect predators. Though smaller in size than many other fossils, this was the first of its species to possess a major advantage.
This is the fossil of a gliding reptile that is about 250 million years old and has the strange name of Coelurosauravus. This reptile actually developed gliding flight.
The ability to glide allows an animal to catch prey in the air, like the giant insects. The planet continued to heat up at the end of the Permian period. Swamps, an infinite source of fossils, now had aquatic plants characteristic of stagnant waters. Like the insects during the Carboniferous period, reptiles were just starting to try out life in the trees and flying. Amongst them, Coelurosauravus would become an outstanding insect hunter, thanks to its retractable wings.
It had a very unusual and interesting anatomy. Its fairly small head was a triangular shape. On its skull, we can see small, conical pointed teeth. They were probably used to crack the hard exoskeletons of insects. And of course, the main characteristic of this gliding reptile are its stick-shaped bones that start around the armpits and enable this animal to throw itself in the air and base jump. We can well imagine it climbing up this microscope, for instance, and then jumping. We can even imagine it climbing with its small claws and then unfolding its wings to glide. So we can picture the race between Coelurosauravus and the flying insects living at that time.
Only 16 inches long, this small reptile couldn't catch Meganeuras, but it could compete for the same prey, the Paleodictyoptera. To catch its victim, it has to take the plunge. Coelurosauravus can't flap its wings. To catch flying insects, it relies on an element of surprise. And its ability to glide. There is no room for error. Coelurosauravus is merely a first step on the road to flight.
This gliding reptile has no doubt played a part, maybe not in the full extension of giant insects, but in any case, we have a super predator regularly attacking them, and we can therefore assume that this was one element in the decline of giant insects at the time.
If Coelurosauravus was not the only culprit, it was certainly the first to put pressure on giant insects before any others took to the skies. This animal guarding the entrance to the Karlsruhe Museum in Germany is part of the Pterosaur family. These flying reptiles appeared 230 million years ago. Today, they are completely extinct, but scientists have discovered around 100 different species. Could they, too, have been a threat to giant insects? Professor Eberhard Frey, or Dino as he is usually known, is a world specialist in pterosaurs.
Pterosaurs are flying reptiles, and they are characterized by a flight membrane that extended from the tip of the little finger down to the ankle. The interesting point with these pterosaurs is that they have a size range which is simply unbelievable, from about 20 centimeters wingspan up to 14 meters wingspan, which is unique.
Yet according to scientists, very few of these pterosaurs were insect eaters. The only insectivores were part of the Anuognathus family, among the smallest pterosaurs.
We cannot imagine really that they hunted the big insects, but probably they chased the small ones which are not seen in the fossil record. The big insects, however, also chased small insects, so they probably conquered about the same prey. All the other pterosaurs from that time we know likely fed on something else and thus did not make any concurrence to the big insects, and probably this is one of the reasons why they persisted such a long time.
230 million years ago, during the Triassic period, pterosaurs spread around Europe, but also to what is now South America and Asia. For the first time in the history of life on Earth, a family of vertebrates learned to master not just gliding, but flapping flight. Like Anuognathus, discovered in Germany, its Asian cousin, Batrachognathus, is a flying reptile, nocturnal, insect-eating, and fast. With its flat skull and big eyes, Batrachognathus occupies the same ecological niche as modern-day owls. But the comparison with birds of prey stops there. Its enormous jaws are equipped with a dozen conical teeth. No flying insect can hide from Batrachognathus volans, literally, flying frog jaw. Can the calligramma, an insect with a 10-inch wingspan, take it on? An experiment carried out in Germany puts the theory to the test. Dino Frey works in collaboration with the Institute of Fluid Mechanics in Karlsruhe, Germany. This wind tunnel is usually used to refine the shape of airplanes and improve their aerodynamics. But today, the paleontologist is using it to test the pterosaurs' flying abilities. A resin and carbon fiber model of Anuognathus is placed in the wind tunnel.
We are at the beginning of our studies, but what we learned so far is that pterosaurs likely were extremely slow flyers. Yeah? So they could cope with wind speeds around 40 kilometers per hour or less. That probably these guys needed to flap their wings to stay in the air, and that they were not very good gliders. But flapping wings also means that they were, as active flyers, much more maneuverable. And this is again interesting when they started to chase insects on the wing.
When pterosaurs appeared, insects lost the monopoly on flapping flight. Batrachognathus was indeed capable of leaving the tree-lined shore to chase insects out in the open, which his predecessor, Coelurosauravus, the flying lizard, was unable to do. The pterosaurs seem to have had more of an impact on the giant insect's prey than on the giant insects themselves, contributing to their final decline, but not fully explaining their extinction. On the other side of the Atlantic, one American researcher suggested other culprits in a study published in August 2012. This paleontologist specializes in the extinction that occurred at the end of the Permian period, 250 million years ago. More at home in front of a computer than wielding a trowel in the field, Matthew Clapham is a database devotee. It took him a year and a half to collect the information needed to publish his survey on the decline of giant insects. He has undertaken a mammoth task, gathering the sizes of all fossil wings since the first scientific publications.
We compiled this very large database with nearly 10,000 insect species by simply getting published papers where paleontologists had found insect fossils and described them and given them a name.
Clapham discovered that during the first part of their history, insect size changed with the level of oxygen in the atmosphere. As oxygen declined, they diminished in size, and as it rose, their size increased.
So this pattern holds for the first 200 million years or so of insect history. But then beginning in the late part of the Jurassic period, around 150 million years ago, you can see insects become smaller, even though atmospheric oxygen is going up at this time. And this coincides quite closely with the evolution of Archaeopteryx, the first bird.
The ancient ancestors of the birds first appeared during the Jurassic period, 160 million years ago. The oldest fossils come from China. At that time, forests of giant conifers offered a fantastic launch pad to conquer the sky. An ecological niche that was quickly seized by a new generation of creatures learning to fly. Small dinosaurs, like this Anchiornis, had feathers on their arms and legs and used them as wings. The claws on their wings enabled them to gain altitude and get good vantage points. Insects, like this Duracimbroflebia, had to hide in the trees to survive. As soon as it takes off, it becomes visible and is hunted down by Anchiornis. While only a few pterosaurs, like Anuognathus, ate insects, all bird ancestors did. Increasingly skilled at flying, they would become fierce insect predators.
In the Cretaceous period, when these first birds are evolving, there would have been increased predation pressure on these large insects in particular, as they were less maneuverable than the smaller insects. In addition to this increased predation, there was likely competition between birds and insects, especially these large predatory insects, for the same food sources. And so both of those factors likely led to a decrease in insect size.
This competition between birds and insects still happens today. Just like flying lizards and pterosaurs, birds would have had an influence on the size of insects. But why have giant insects completely disappeared, leaving only today's small insect population? A last clue could provide an answer. It came from a fossil-rich site close to where Anchiornis was found, in the Chinese region of Liaoning, northeast of Beijing. The numerous eruptions that shook the region 125 million years ago have helped preserve certain plants from the period in volcanic ash, including the ancestors of flowering plants. Discovered in 2002 by the paleobotanist Sun Gay, they would have had an unexpected impact on the extinction of the last large-sized dragonflies.
But here in China, in the West Liaoning, we found all this known angiosperm we call the Archaeopteryx.
This is Archaeopteryx, the first flower to appear on our planet. On this fossil, seen through a microscope, we can distinguish the male organs, the stamens that contain the pollen, and the pistil, the female organ. These characteristics allow Sun Gay to confirm that this fossil belongs to the angiosperms, a family of plants whose seeds are enclosed inside a fruit, unlike conifers. According to the paleobotanist, these plants were aquatic and grew on lake shores. But what does the appearance of the first flowering plants have to do with the extinction of large carnivorous insects? André Nel believes these two events are linked.
Many families of insects disappeared at that time, and others managed to adapt to angiosperms, which proliferated and began to diversify to produce more or less our modern forests. The impact was also very significant for dragonflies during that same period.
Could the decline of giant insects have something to do with the dragonfly's original shape? Because before they were able to fly, they were aquatic creatures. Their life began underwater. For the first few years, they existed as larvae. And just like their cousins, the mayflies, they fed on other aquatic insect larvae. When flowering plants, such as Archaeofructus, appeared on the lake shores 125 million years ago, the larvae's life conditions changed. The plants took root in shallow waters, but then opened their flowers in the air. When they withered, their petals and leaves floated on the surface before sinking to the bottom. This material is digested by the microorganisms present in the water, but to do this, the organisms use the oxygen contained in the water, leaving little oxygen available for the dragonfly larvae.
These dragonflies may have disappeared at that time because their larvae could not adapt to this change in the aquatic ecosystem, and they were replaced by other dragonflies.
The emergence of flowering plants completely modified the lake's ecosystem and would have led to the extinction of the last large-sized insects which had gradually declined since the Carboniferous. The extinction of arthropods and giant insects over millions of years of evolution teaches us that it took many protagonists to cause the extinction of these species. The change in the composition of oxygen in the atmosphere, the emergence of new predators like flying lizards, some pterosaurs, and the bird ancestors, and finally, the birth of flowers. In the early 21st century, which are the largest insects that inhabit our planet? Today, insects can reach the size of a hand, but very few are bigger than this Chinese cricket. For we are at the dawn of a new phase of extinction, caused by humans, since the onset of the Industrial Revolution.
The large insects live mostly in tropical or intertropical climates. They're in danger since their habitat is at risk. If the forest in which the giant stick insect lives is in danger, the giant butterfly will of course disappear.
I certainly hope that we will continue to see them, but certainly with the rate of habitat destruction that's going on throughout the world, particularly in the tropical environments where many of these species occur, it is very likely that a lot of them will be lost, just like the giant insects.